Welcome to another session of microwave and antennas part. So in previous session, we had discussed regarding microwave network theory, in which our discussion in the previous session was related to the properties of S matrix or the scattering matrix, in which we saw that when do we come across the diagonal elements to be zero, that is when we have a matched network. Then what happens when we have a lossy, that is a lossless microwave network? What happens to the S parameters when we have a reciprocal network? What are the S parameters which we obtain? Then apart from that, we observed that the S matrices will be square in nature. That is, it will be a square matrix. Then apart from that, we could see that the diagonal elements of a S matrix provides you information pertaining to the reflection coefficient at the respective port, and the other parameters provide the, that is a non-diagonal elements, provide the information pertaining to the transmission coefficient. That is what we had seen in the previous session. So now moving ahead, let us discuss the next part. So we can look out how S matrix and Z matrices are related to each other. So in this case, we can just see how we can obtain the relation between S and Z matrices. Now remember, Z matrix is associated with the input voltage and the output current, whereas the S matrix is associated with the incident amplitudes and the reflected amplitudes. So it has to have two parameters. One is associated with the incident parameter and the reflected. So now by analogy, what we have is plus is used, that is the subscript plus is used for identifying the incident parameter, and minus is used to identify the reflected parameters, whether it is current or the voltage. If you just observe here, we have a plus. This associates with the incident parameter. This associates with the reflected parameter. So now, based on the previous discussions, we had seen that voltage at any port, say K is the port what we are looking at, the voltage at port K will be equal to the sum of the incident and the reflected voltage at that port. So which is given by the current and the impedance at the respective ports with this equation, that is Vk is equal to Zk1 I1 plus Zk2 I2, so on up to Zkn In, where n is the number of ports which are present. So therefore, when it is represented in terms of impedance, this is the equation what we will be having. And now we also had seen that what is the overall current equal to? Overall current is actually equal to the incident current minus the reflected current. So which in terms of the intrinsic impedance can be written in this form. So which is actually Vk plus divided, that is the incident voltage divided by Z0 minus incident voltage divided by, reflected voltage divided by Z0, which gives you this equation for the current. And when you simplify this, this is the result what you get for the current representation in terms of the voltages. So now here we can see that based on this equation itself, I can write Vk plus, that is the incident voltage parameter, is equal to, you take the reflected component on the other end, we have it as Z0 Ik into the reflected voltage plus the reflected voltage. Now, what is this reflected parameter in terms of the incident voltage? So that is what we are looking out here. So this is the replacement in which we observe that Vk minus, that is the reflected voltage, is equal to total voltage minus the incident voltage. So that is being replaced over here, and we obtain this overall equation. Now in this case, what we are doing is we are obtaining a representation for the incident voltage and the reflected voltage in terms of the Z0, Ik and Vk parameters. So based on this, we can have the representations for Vk plus. So this is actually Vk plus. We have the representation for the incident voltage, which is given over here, which is half the total voltage at port K plus Z0 into Ik, which is the current at port K. So now Vk, we had seen that in terms of the impedance parameter, it is given by this equation. So when you substitute that over here, this is the final equation what you get for the incident wave parameter. That is the incident voltage uh, representation. So this is the incident voltage. Similarly, on the similar basis, when we try to obtain the representation for the reflected voltage, so because of the symmetric nature of the equation, you can see that we can obtain the value which will be as shown here. It will be nothing but half into Vk minus Z naught into Ik. So and Vk you have substituted with the summation what is represented over here. So these are the two equations what we have obtained for Vk plus and Vk minus. So now here we can see that when we represent this in the matrix form, or else if you expand the equation, if you expand this equation and try to realize what are the parameters, if you expand this entire equation and try to realize the parameters. So if you just observe if k is equal to 0, so what we have is Z naught j ij minus Z naught into I naught. So here, if I keep on substituting for different values of these parameters, that is k is equal to 0 to n. If I keep on substituting this, I'll be having all the equations. I'll be having say n plus 1 number of equations. And if I represent those in terms of the a matrix form, right? We will obtain a matrix in which we'll be having like say V naught plus V1 plus. So we'll be having equations for all these up to Vn plus. So and substituting this in appropriate equation, we'll be obtaining the equations for the incident parameters. So now what we do is we can represent these in terms of the matrices. So how we used to say refer to the V is equal to Zi. That is the matrix representations of Z parameters, if you remember. So if we have two voltages, that is V1 and V2, this one we used to identify with the parameter which is identified as V over here. So which is a matrix which contains of V1 and V2. So similarly, we have Z11, Z12, Z21 and Z22 with the current parameters. So this is for the two port. Now this is in general when we consider this, how we can represent this overall representation is, so this will give you the association of all the reflected, sorry, incident wave parameters, which is obtained from this equation. So incident parameters, which is obtained from this equation. So it is equal to half. And here we see that this, when we try to simplify and obtain the its equivalent representation, we obtain it as Z11 plus Z0. All the diagonal elements, where if you just observe, will be having the intrinsic impedance added to it. It will be Z11 plus Z0, Z22 plus Z0, so on up to the nth port ZNN plus Z0. And the remaining elements will be Z12 up to Z11N and so on. So these are this is the representation of this matrix, gives the representation associated with the impedance parameters over here. And when we take out the common parameters, I'll be having the current parameter, which is actually given by I1, I2, so on up to IN. So this is the representation which we obtain for the incident parameter. Now, similarly, we can obtain even for the reflected parameter, this thing we can obtain, in which it will be Z11 minus Z0, Z22 minus Z0, and ZNN up to Z minus Z0. So here, what we do is now, if I just observe this, this is nothing but matrix Z plus the unitary matrix or the identity matrix, plus the identity matrix. but this matrix is multiplied with Z0. So this will give you Z11 plus Z0, and other elements, since they will be 0, it will be only Z12 up to Z1n, and it follows with the rest of the elements. So now in this case, what they have done is they have represented it in the matrix form. So here, this one will be equivalent to the matrix Z plus the unitary matrix, which is multiplied with the characteristic impedance Z0. And this matrix is multiplied with the current parameter. That is matrix which represents the current. There is a total current at the respective ports. So now here, this one, if I want to represent, right, what I can do is I can take this parameter on the left hand side and make the adjustments, and I can see that I'll be having the representation for current, which is given by 2 into this matrix is inverse, that is, it is the inverse of this matrix into the incident parameters. Now on the similar lines, we can obtain the representation for the reflected waves, that is the reflected voltages. So in which, if you just look at the symmetry, what will be the change? It will be Z minus. So this part will be the change. It will be minus unitary matrix multiplied with Z0. So that is what you will be getting. So now here what we are doing is we are trying to obtain a relation between V minus and V plus in terms of Z parameters. That is what we are trying to obtain here. So first we identified the total voltages can be represented in terms of incident and reflected voltages, current in terms of incident and reflected current. Then this was represented in terms of the voltages, that is incident and reflected voltages. So once we obtained these equations, we tried to separate the representation for Vk plus and Vk minus. So once we obtained the representations for Vk plus and Vk minus, we represented those in matrix form, keeping Z parameter as it is based on this equation by making the necessary adjustments. So here we have got for V plus and here we got for V minus. So now here you can observe that I have current I. Now since I want the relation between V minus and V plus, what we can do is we can substitute I with this equation. So when we substitute I with the equation which is represented over here, what we obtain is we obtain, so that is Z matrix minus the unitary matrix multiplied with the characteristic impedance. This entire matrix multiplied with this parameter, which is identified by this equation. So which will be given as Z, that is matrix Z plus unitary matrix multiplied with characteristic impedance. That is this parameter. 2 actually get cancelled over there. So once they are cancelled, we are left out with this parameter. So what is this giving? This is giving you the relation between V plus and V minus, that is incident and reflected and the incident voltages. Now in previous sessions, if you remember, we had obtained, say V1 was obtained as V1 plus divided by square root of Z0. And if I wanted B1, it is V1 minus divided by square root of Z0. That is in the previous session we had discussed regarding these parameters. So similarly, if I want any of the ports, say if I want some AK, so it will be volt, that is at port K. So it will be the incident voltage at port K divided by square root of Z0, and for B1 it will be the reflected voltage at port K divided by square root of Z0. So this is based on the previous discussions or the previous sessions what we had seen. So now what we are doing is, since we have obtained V minus over here, if I divide this with square root of Z0, on RHS and LHS, I divide this with square root of Z0. What we obtain is, this is nothing but the representation for the incident wave amplitudes. And this one gives you the representation for the, this one gives you the, B gives you the reflected wave amplitudes, and this parameter what we observe gives you the incident wave amplitudes. So that is what is represented over here. So we have the reflected wave amplitudes, which is equal to Z minus Z naught into U into Z plus Z naught into U, its inverse. This is multiplied with the incident wave amplitudes. So, but we have seen that B is equal to S into A. And here, if you observe, this is nothing but the matrix S. So from this one, we can observe that the matrix S in terms of Z parameters can be given as Z minus Z naught into U into Z plus Z naught into U, its inverse. So this is how we represent the overall equation. So here we can take Z naught common in both. So since this is inverse, if it goes to the denominator, Z naught gets cancelled. And what we are left out is matrix Z divided by Z naught minus unitary matrix. That is this for this parameter. And for the inverse, this thing, it will be matrix Z divided by Z naught plus U, its inverse. So this is the relation between the S matrix and the characteristic impedance matrix. That is, sorry, the impedance matrix. So now on the similar lines, we can obtain the relation between the S matrix and the Y matrices. That is the scattering matrix and the admittance matrix. So again, on the similar lines, what we do is we first represent the total voltages and the currents in terms of the incident and reflected voltages which are present. So based on that, we can have the representation for the current I. So in impedance, we make use of Y into V. That is, I is equal to Y into V. In say impedance matrix, we make use of the equation that is Z into I. Now here in admittance, we make use of this equation. So therefore, we represent the current over here. So in this case, we obtain the equation for IK, which is represented over here. So now what we do is we represent VK plus and VK minus separately. That is how we have done it for this parameter, right? So what we did, we represented these two parameters and two equations we had, and we separated VK plus and VK minus. That is, we obtained separate representations for VK plus and VK minus in terms of the matrix Z. That is this matrix. So we had two representations. So on the similar basis, using these two equations, what we try to do is we obtain the representation for V plus and V minus, and then make use of, that is, these two are represented in terms of the admittance parameters. In terms of admittance parameters. So based on that, again you simplify, and when you simplify, you will be able to obtain the representation for the matrices of incident and the reflected wave amplitudes as V plus and V minus, which is represented over here. Now, since the networks will be symmetric, what you can observe is here you can see that we have Z plus Z naught into U, its inverse, and for this one we have Z plus Z minus Z naught into U. So here also you can observe that we will be obtaining the same parameter Y plus Y naught into U, and for reflected we'll be having Y minus Y naught into U. So just the you should be just check out because of the symmetry you have this kind of equation. So here it will be in terms of voltages, there it will be in terms of the currents. So now when you simplify the overall representation, when you simplify this overall representation, so in this case what you have to do is you have to represent what is V equal to in terms of matrix V plus, that is the incident parameters. So you take it at the other end, you will be getting the inverse, you multiply these parameters, and in the end you will be getting the substitution. So here you will be having V minus, which will be represented with this overall parameter. So when I make the comparison, what I'll be having, I get to know that again, I divide this by square root of Z naught, this one by square root of Z naught. So this one gives me the parameter which is associated with the reflected wave amplitude. and this one gives me the incident wave amplitude. So and the remaining parameter what we are having, it gives you the S matrix. So here we can see that S matrix is associated with or it is related with Y matrix with the equation what we have shown over here. So these are the representations what we are having. So if you just compare it with even this case also, right? It is Z minus Z naught. So here if you just check Z by Z naught minus U into Z by Z naught plus U, its inverse. So in this slight change, it will be U minus Z by Y naught. So in Y matrix, when you're comparing, so when you simplify, you'll be able to obtain this overall result. So it will be U minus Y by Y naught into U plus Y by Y naught, its inverse. So this is what you will be obtaining for the relation between S and Y matrices. In next part, we'll discuss regarding what are the properties which are found common between S, Z, and Y matrices. So if you just observe, if I am having say a two-port network, if I'm having a two-port network, S matrix will be of the size 2 by 2, Z matrix also will be of the size 2 by 2, and Y matrix also will be of the size 2 by 2. So what is this indicating? Each case, say S matrix will be having 4 elements, Z matrix will be having 4 elements, and Y matrix also will be having the 4 elements. So that is what is specified over here. That is the number of elements will be equal to that is depending on the ports will be equal in all of these three matrices. Now, if the device or the network is reciprocal in nature, so if it is reciprocal, we can see that how Z, Y, and S parameters are related. So that is in this case, Zij is equal to Zji, and similarly Sij is equal to Sji. So because of this equation, even I can specify Yij is equal to Yji. So in other forms, what it specifies, if I multiply a transpose with its complex conjugate, I should be having a identity matrix or a unit matrix. So that is what it implies. So this, if the network is reciprocal, then it satisfies the condition for all these three. That is for S, Z, and Y. That is Zij is equal to Zji. Similarly for S matrices also it will be Sij equal to Sji, and even for Y matrix also it will be satisfying the same condition. Now, if Z is symmetrical, so if it is symmetrical, then it also implies that S also will be symmetrical. So if I obtain the condition that Z is symmetrical, then we obtain even the condition that the S matrix also will be symmetrical in nature. So now, what are the advantages of S over these two parameters? So in the previous case, we had seen that why we cannot go forward with a direct estimation of Z and Y. It is because of the open and short circuit conditions, which are difficult to obtain in microwave devices. So it is because of that we cannot go directly with these aspects. But what are the advantages of going ahead with the scattering parameters at high frequency range? So here, what happens is when we are applying the conditions to obtain the S parameters, right? The source basically remains constant. That is in terms of power, what we are talking. The power is unaltered. That is what we look out for. Then apart from this, what happens is the parameters what we can measure using S matrix is associated with the VSWR, that is voltage standing wave ratio, the power parameter, and the phase parameter. So this is nothing but you can observe that it is B by A. This gives you the reflection coefficient. From reflection coefficient, I can obtain the S parameter. The VSWR value. We can obtain the VSWR value. If you remember, it is given by 1 plus reflection coefficient divided by 1 minus reflection coefficient. If this is giving the reflection coefficient parameter, that is if I have something as B1 by A1 or B2 by A2. So these give you the reflection parameters. That is the diagonal elements in the S matrix. So if I get to know what is the reflection coefficient, I'll be able to obtain what is the VSWR parameter, and other parameters I can obtain based on the transmission coefficient values. And then starting discussions, we had seen that the values of the amplitudes what we are considering, they are normalized in such a way that when you consider the square of the incident or the reflected wave parameters, they give you the average power which is associated at that port. So therefore, these are the parameters what you can look out for when you are dealing with S matrix. But such kind of measurements are not possible when you are dealing with Z and Y representations. So it is difficult to measure these things when you are dealing with Z and Y parameters. You have to do a calculations over there, and then you need to obtain all these aspects. Then if you check that if S matrix satisfies the unitary matrix, that is, then it is indirectly indicating that the network is lossless. The network is lossless. So if the network is lossless, then it gives an indication that there is a power balance between the input and the output, what you are observing. But such kind of check I cannot have with the Z and Y parameters. So we cannot have check with respect to Z and Y parameters. But I say I measure all the parameters, say S11, S12, and so on. All parameters I measure, and I see that it satisfies the unitary property. So indirectly, I get an indication that the network is actually a lossless network, which is satisfying the power balance condition. Now, apart from this, we had seen the phase shift property of S matrix. So in S matrix, what happens is if you have if you have a two-port network, for example, say you have measured the parameters at planes which are mentioned with 1 and 2 over here. Now what you do is if you shift these two by certain length, say this one you're shifting by L1 and this one you're shifting by L2. And these are the new reference planes at which you are measuring the parameters, that is the S parameters. Now in S parameters, what happens is if you're measuring by altering the distance, right, only the phase changes. Only the phase changes, magnitude remains same. So if I'm measuring S11, its magnitude remains same, only the phase will be altering. Whereas if you do the same thing, that is, if you slightly change over the measurement distances, right, in when you're measuring Z and Y parameters, what happens is if you change this, both magnitude and phase, both are altered when you're shifting the points at which you are measuring the Z and Y parameters. Whereas in S parameters, what happens is it is only the phase component which alters, but the magnitude remains the same. So these are just a few things to note down in case of the properties associated with S, Z, and Y. So which are common, and what is the advantage of S over the impedance and the admittance parameters. So we'll be coming to this part later. So now let us move ahead and discuss a few other things. Next part, what we have to look out is we'll be discussing regarding microwave passive components. So now, as we have active and passive components at low frequency, even at high frequency, we have the same kind of components. But what are these components? So here, how do we classify the components as active and passive? So if a component or a device is capable to deliver power or energy to a circuit, if it is able to generate its power and deliver it to a circuit, we call such elements or components as the active components. Now in passive components, what happens is it basically utilizes the power which is provided. It cannot provide the power to the circuit, but it utilizes the power which is provided. So these fall under the passive component type. So in this case, again, if I just consider the examples, right, we have diodes, transistors, SCR, integrated circuits, which form the active components. And passive components, here you can see that resistor, capacitor, inductor. Now, if I just observe from other point of view, in resistor, what happens is you lose energy in the form of heat. In capacitor, you are storing the energy. say you're storing with the help of the capacitive material, and inductor you are storing the energy in the form of say the magnetic field. So whenever so here you can see that either the energy is dissipated or it is stored. So that is what you can observe in passive components. They are stored or they are dissipated. But in this case, that condition doesn't come. So in active components. So now here, what are the function of the active components? The devices basically produce the energy which is in the form of voltage or current. So even in this case also you require a source. Even in microwave devices you require the source. So it is those components which act as source will be acting as the active components, but the other components which make use of these will be classified as the passive components. So they store or dissipate the energy in the form of the voltage or current, that is in indirectly if you just see it will be in the form of electric or magnetic field. So these are a few things to note down. Then power gain, you'll be able to obtain the power gain in active components, whereas in passive components will not be able to obtain the power gain. Now, apart from that, what will be the flow of current in active components? We can actually control the flow of current, but in passive components, we cannot control the flow of current. For example, if I consider the diode, so in diode, it will be operating in only one direction. That is when it is in the active zone. So in but when it is in the reverse bias condition, it will not be operating. So you're basically controlling the direction in which the current flows. So such kind of operations are possible with active devices. Then a requirement for external source. So these itself can be acting as a source and they can require the external sources for its operation. So diode, if I have to make use of this diode, I have to provide a supply for this. But in this case, what happens is they do not require the external source. Suppose I have charged the capacitor and have got it out, so it can store the energy. So in that moment, there's no requirement of the external source for its operation. So here, the active components basically act as an energy donor, whereas the passive components act as a energy acceptors. So these are just a few things to note down with respect to the active components and the passive components. So next point, what we will be discussing is regarding coaxial connectors and the adapters. So here you can see that the name itself tells that these are the connectors, or they are used for the adaptation purpose. So these connectors are nothing but they are used for connecting, say, the cables, coaxial cables, or they are used to connect different cables together. So we basically use for connecting the coaxial cables. That is, coaxial connectors are used for connection of coaxial cables. Now here we can see that there are different kinds of cables which we can see over here. So in this one, say N specifies navy type of connector. Then we have BNC, which basically tells that it is say a Beyond Navy connector. Beyond Navy connector. Then we have TNC, which is threaded Navy connector. Then we have SMA, which is submersive version A type of connector. So these are different kinds of connectors what we can observe here. So they are used for these purposes. Now here we can see that we can again have classification as male and female, or in some cases we don't have that classification, that is male or female in this case. So what happens is if you just observe how they are classified as male and female, you can look at the threadings which are present. So in this case, if you just observe, the threadings are present inside. So if you want to connect to coaxial cables, right? You'll be having the threads inside. If you have these threads inside, it is called as a navy male connector, and here you can see that the threads are present outside. So in these kind of devices will be classified as the female connectors. In few, this thing you'll not be having both, that is like, for example, you have APC 7. So you will not be having the specification regarding the connection, whether the threading is outside or inside. So that in such cases, we can that is you can see that in sometimes we just have a hook wherein we just rotate. Say on the CRO, you might have observed those things. You rotate and they both get connected. You don't have the threads which are present over there. So those kind of we classify them as neither male or nor female. So now apart from this, you can see how the cross section of SMA male schematic and female schematic is shown. So here the main observation is, here you can see that the threadings in the female SMA connectors, this is threading is outside, whereas for the male connectors, the threading is inside, say inside this tube. So using which is used for connection. So here we can see a few of the types which are specified, like we have the N, that is the navy type of connector, the threaded navy connector, then submissive uh, version A connector, then APC we have. So these are few things to note down. So these are again classified. They can be either male, female. APC is cannot be classified in either male or female. Then this one can contain both. It can be used as a male or a female connector. Then what is the dielectric material they'll be utilizing for the connection? It will be you can see for the navy connector, it will be air, and for these two, the dielectric material will be air, whereas for the others, it will be a solid element which will be utilized. And generally the impedances, that is the for matching which is used, they provide an impedance of around 50 to 75 ohms. They provide 50 to 75 ohms. So this is associated with uh, the coaxial connectors and adapters. So next, we can look at what are the attenuators. So the name specifies that it's attenuator. So what is its purpose? Its purpose is to reduce the strength of the input, to reduce the strength of the input. So these are actually passive. Even the coaxial connectors are passive devices. Uh, and attenuators, these are actually the passive devices which are used to control the power levels in the microwave system. How they basically look into the controlling the power, they by absorbing, they partially absorb the power which is being transmitted from one end to the other end. So that is how they try to reduce the or introduce the attenuation into the signal which is being transmitted. Now in attenuators, again, we have two kinds of attenuators. One is called as fixed attenuator and one is called as variable attenuator. So here you can see that in this figure, we have a resistive film or a resistive element. So what is this resistive element? It basically has a aquadag coating. It has a aquadag coating. So what this does is, whatever signal is passing through this, it'll this aquadag coating, that is the resistive film which is present, it tries to absorb the signal energy and then pass it at the other end. So this is what is happening in this case. Now in this case, what is happening is this element is fixed at one point. It is fixed at one point. Say on from the wall of the waveguides, you can fix it. So once it is fixed, it will provide you a fixed attenuation. Now in these two cases, you can see that the attenuation is actually variable. So in this one, you can see that from one wall mount, you have a resistive film. So at these two ends, so you have a resistive film, and this is basically placed in a direction which is perpendicular to the, or it is placed, when I consider this, it is actually placed in parallel with the electric field. So now in this case, what happens is, since in this one it was fixed, now what I want to do is I want to introduce different attenuations in the same waveguide what I am using. So in order to do that, what is done is a screw gauge is attached, and by a movement of the screw gauge, this resistive element moves towards the center of the waveguide. So as it is moving, what happens is it introduces more and more resistive element into the waveguide. So if that is happening, what happens is more and more attenuation will be introduced. And here you can see that this resistive element is present. Now these slant, this thing you can observe that they are positioned at some angle. So now this is basically done to avoid reflections. They try to minimize the reflections due to this introduction of the resistive films. Otherwise, what happens is the parameters what we discussed, say S parameters, will be changed for the overall network. So we have to take care of those things also when we are dealing with say any of the elements what we are introducing into the network. So in this slant, this thing is to avoid the reflections which are being generated. So you're trying to minimize those reflections. So that is what you can look out in this attenuator. So similar kind of attenuator I can have, which is represented over here. So in this one, what you can see is on top of the waveguide, you have the attenuator which is placed and you have a flap. By the movement of the flap, we can either increase the attenuation or decrease the attenuation of the signal which is being provided as input to this attenuator. So this is a variable kind of attenuators what we can observe, that is B and C are the variable attenuators, and this one is a fixed attenuator. And this example is basically for the coaxial line, and this one we can observe in the waveguides. So next we have a precision variable attenuator, which can be of this kind, which can be represented over here. So now in this one, what changes you can observe is you can see that we have two kinds of waveguides. That is, one is a rectangular waveguide. One is rectangular waveguide, and we can have circular waveguides. So now in precision variable attenuator, you can see that this part is circular waveguide, whereas here you can see that you have a rectangular waveguide. Now, why this comes is in majority of the cases, when we are dealing, we come across with both kind of waveguides, that is circular or rectangular waveguides. So when we are say having rectangular waveguides and I want to use the precision variable attenuator, so for that I require these kind of connections which are present. So here what we can observe is we can observe that there is a transition from rectangular to circular, that is RC1 and RC2. They represent the rectangular to circular transitions. And in rectangular mode, right, for in waveguides, we will be operating at TE10 mode. But when you move to the circular, right, it turns out to be TE11 mode, which will be operating. And here the main attenuation element is this element, that is R2, the resistive element which is present over here. Now, how the attenuation is introduced? It is introduced by with the help of this resistive element which is present within this circular waveguide, which is actually present between these two transitions of RC1 and RC2. So now here what happens is the electric field which is being inserted, that is which is being given as input at one end. What happens is it will be having two components. One is E say sine theta and the other one will be E cos theta. So these are two components which will be present. Now in attenuator, what it does is it tries to minimize based on its orientation. It tries to minimize one of these components and the other component will be held as it is. So it is because of this, what happens is you will be having only one component which is present. Say, for example, if I consider this and if it is at 45 degrees, if this resistive element is rotated at 45 degrees. So what happens is this E cos theta component becomes zero. E cos theta component becomes zero. And we are left out with only E sin theta. So that will be the component which will be available at the output of this attenuator. Along with this, what happens is you will be having a sine component which is present over here. So output of this overall structure will be given by E sine square theta. It will be given by E sine square theta. So in attenuator, what you are introducing E over here, and the attenuated part will be giving you E sine square theta. So the overall field will be attenuated by the value which you obtain over here. So that is what you'll be getting in the precision type variable attenuator. So now what is the attenuation which you will be introducing? It is given by alpha, which is what is the input power divided by what is what is the input field divided by the output field. So when you try to simplify this in terms of S21, we'll be obtaining alpha as 1 divided by magnitude of S21. And when we try to represent it in terms of dB, this is the value what we will be obtaining. Now, if it is symmetric, we can obtain these representations. So here what we have is, if you just observe what is S21 equal to, S21 is actually equal to sine square theta. Now S11 and S21. So here we try to minimize the reflections. So in that case, what happens is the reflection, since it is a two port, we have one input port and one output port for this attenuator. So generally the attenuators will be a two port device. So we'll be having total 4 parameters, that is S11, S12, S21 and S22. Since we try to see that the reflections are minimum, it indicates that R1, that is reflection coefficient at port 1 and reflection coefficient at port 2, both are 0. So this gives rise to what S11, which is equal to 0, and S22, which is equal to 0. So that is what is specified over here. We try to minimize the reflection coefficient as much as possible. So therefore the S matrix can be represented in this form, whereas S11 is 0, S22 is 0, whereas S21 is sine square. But since if you just observe that it is symmetric in nature, it implies that if S12 will also be equal to sine square theta. That is, if you insert input at this end and you observe the output at this end, even then it will be operating in the same way, and the circuit, that is the network, will be symmetric. So this is with respect to the variable precision variable attenuator. So in the next session, we'll be looking out the phase shifters, and last part we'll be looking out for the waveguide T's. So these are the things what we'll be discussing in the coming 4th sessions. So for today, this is all what we have. We'll meet in the next session. Okay. Thank you.